Today we will look at how to deal with the interactions of electrically charged fermions. So, let us summarize first what we have learned so far in the particle physics part of this course. So, we have said that in the relativistic case, when we are dealing with particles which are moving at or having high energies and moving at relativistic speeds, then we have to consider the evolution equation or the equation of motion different from that of the Schrodinger equation. And what we found is the Klein-Gordon equation as one of the suitable equations to describe the dynamics of particles, including their relativistic kinematics. So, this in the notation that is now familiar to us, I will write this as dou mu phi plus m square phi equal to 0, where phi is the wave function that represents the charged particle. This is a equation which is quadratic in the derivative, both time and spatial derivative. Let me, for completeness sake, write what this means. This is partial derivative with respect to time and the gradient operator. This we have not included the factor of c, which is usually there, to keep both the terms at the same dimension. So, usually it is written as 1 over c this thing, but we are using a system of units which is in which c is taken to be 1 and the Planck constant h cross is equal to 1. Now, this is basically the Klein-Gordon equation describing whatever particle that is represented by the wave function phi. Now, Dirac equation is again a relativistic description of elementary particles or the particles. This free particle, the one that we have written down phi, is also considered as a free particle. There is no potential, there is no interaction, there is only this mass term and the time derivative telling us how this free particle will evolve with time, and the kinetic energy part described by given by the gradient of that. In Dirac equation, we have a slightly different case, where we have gamma mu, an object which we have defined clearly and described in detail, in some detail, and I dou mu, which is essentially the momentum operator apart from a sign and apart from the constant h cross, which we are taking as 1, this acting on psi, okay. This minus m psi is equal to 0. So, that is the Dirac equation. So, the differences between these two, which we have already gone through, but let me just remind you, gamma is a 4 by 4 matrix and let me denote the indices, matrix indices explicitly, this I dou mu, which is not any matrix, but psi is a matrix, which is a single index, that is it is 4 by 1 matrix. So, you have a 4 by 4 matrix multiplying a 4 by 1 matrix. So, that is what we have, minus m psi a. So, this is for each component of this a component of psi and a component of this product. Now, there is a conjugate equation that I can describe, which is important in our case. In the earlier case, the conjugation was just a charge conjugation operator, and psi phi would go to phi star, that would do. But in this case, we have the Hermitian conjugate equation. So, that is basically I dou mu psi, an object which we will define in a minute, psi bar, and gamma mu, this if it is A, then A B minus or rather plus m psi bar B is equal to 0. So, the psi bar is defined as psi dagger with a gamma 0. So, psi bar B is A B. Psi itself, as we saw, is psi 1, psi 4 component object, psi 1, psi 2, psi 3, psi 4. So, this A and B runs from this is the summary of things that we have kind of discussed in the relativistic quantum mechanics or relativistic particle dynamics. We are dealing with free particles, which means particles like electron, which is freely propagating in the space without any electric field, in a region without any electric field or any other field. That is described by this equation. That is the kind of picture that we have. Now, today, as we promised, we are going to look at how interaction can be understood. We had already seen how that is done, understood in the case of particle which obey the Klein-Gordon equation. So, just to summarize or to give in a very short way what is the difference between these two, that without going into any details, let me introduce another word, field. Field and wave function I will use interchangeably, somewhat loosely. So, in relativistic quantum mechanics, we usually call this wave function, whereas a proper mathematical treatment is done in the framework of quantum field theory, where we will actually have to promote these wave functions to what is called the fields. So, there are some subtle differences, but I do not think we should worry about that at the moment, and that will actually take us a little deeper into the aspects which are beyond the course's description. This is a good representation of any scalar particle, a complex field, okay, phi which obeys the Klein-Gordon equation is a good representation of the scalar particle. Whereas, fermionic field like electron is represented by the Dirac equation. It is not, there are certain features, the spins of this is not going to be adequately addressed in Klein-Gordon equation. Okay. Therefore, one has to actually consider the Dirac equation to treat the electron with including its spin part. So, let me not go into any more details of that. We will assume that electrons and particles like electrons, the fermionic particle, half integer spin particles obey the Dirac equation, and usually they are represented by this psi with 4 components like that in the Dirac notation. Whereas, phi is just 2 degrees of freedom here. It is a complex number, one real part and one individual part. So, let me consider the Kg equation or the scalar particle. When I say scalar wave function, that is a wave function which obeys the Klein-Gordon equation. Okay. So, let me write in bracket Klein-Gordon equation and represented by phi. Now, when a current of this phi, a phi particle represented by phi moves, that can be thought about as current. By the way, complex scalar particle represents the charged scalar particle. Okay. So, this current let me denote by letter J mu, and supposing there are photons or the electric field in this region, this notation is also familiar to us. So, J mu interacts with this. In a graphical way, we can represent it in this fashion. There is a current of phi and then there is electric field, electromagnetic field, we represent it interaction by this thing, where J mu is equal to, there is the zeroth component which is rho and represented by rho and j, and rho itself is defined as minus I, sorry, rho itself is defined as I phi star time derivative of phi minus phi time derivative of phi star E minus I E. This can be interpreted as the charge density, electric charge density, and J is represented by I E. Here it is a plus, it is minus I E, and phi star gradient of phi minus phi gradient of phi star. Interpretation here is the current, that is the electric current itself, that is represented by this J. So, in a sense, if you look at the electrodynamics, the Maxwell's equations and all the classical electrodynamics, this notation is clear there. We usually represent charge density by rho and we represent the current density by J. Okay. So, that is what we have here. So, this part we had discussed earlier. So, in case you have forgotten, maybe you can check the previous lectures. Now, coming to so for electron, it is, I think I made a sign earlier, correct sign, and this should have been for electron with minus E charge, it is minus IE. Okay. Sorry for that. Now, what about the fermionic fields? So, fermion represented by psi, they obey Dirac equation. Again, picture is the same. We have a current and the current is interacting with a. So, this is like an electron, and on the way it encounters electromagnetic field, and then how does it interact, and then that is the way we represent it. So, this is again we can do in the same way. The only thing is what is J mu. Here J mu is for electron minus psi, the charge of that, psi bar gamma mu psi. So, psi bar is known, gamma mu is the Dirac matrix, and psi is the wave function. Now, this again when we write it in terms of the charge density and current density, we have rho equal to minus E psi bar gamma 0 psi. Okay. This is nothing but minus E psi bar itself is psi dagger gamma 0. Okay. And then there is another gamma 0 psi, which is equal to minus E psi dagger psi, since gamma 0 square is equal to 1. J is equal to minus E psi bar gamma vector psi. When I say gamma vector, is basically gamma vector is defined in a sense as gamma 1, gamma 2 and gamma 3. We will go back and remind ourselves about one thing, that is the electromagnetic field itself. The electromagnetic field itself has the Maxwell's equations. Maxwell's equations were written as dou mu f mu nu equal to j nu, where j nu is the current density, okay, the source of the electric field, current density of the source of the electric field, and we can write it in terms of rho and j. Okay. And that is what we have in the classical electrodynamics case. F mu nu are the field tensors, which we are again familiar with, we had discussed it earlier. So, this is what it is. This can be written in terms of F mu nu is essentially dou mu in terms of the potential or the photon field, it is dou mu dou nu A mu. And when you put this back, we have dou mu A nu, okay, minus dou mu A mu, dou mu dou nu A mu, okay, equal to j nu. But this, if you focus on this, then this is essentially, there is no preferred order in which this differentiation need to be done, and this can be interchanged. I can do this differentiation first and this the second, or rather I can actually simply change this order in which these two act on A and nothing changes. Now, I have something like this. We can choose this A, so that dou mu A mu is 0 always. Okay. So, this is something which we will assume now, or rather it is something which we had discussed earlier. So, we will say that our A, we have chosen an A which has this particular condition satisfied, that choose A so that dou mu A mu, that is basically the dot product between these two, or the 4 divergence of A vanishes. This can be done always. You can choose A mu without, and that will not change any of the physics aspect, the meaning that it is the same electric field. Any given photon, electromagnetic field can be represented by some A, which can always be written in terms of some divergence less A. That will give you dou mu A nu equal to J nu, or this will give us a solution. Okay. Without going into the details, we can find a solution. This, remember, what do you mean by solution? This, for a given J source, the electric field, electromagnetic field everywhere represented by A mu satisfy this equation. That is what you have. Supposing you have an electron or some distribution of charge, moving distribution of charge, something like that, or a nucleus moving, that will create an electromagnetic field surrounding that. Now, what is that electric field? That is represented by A. How does it behave? That is dictated by this equation. So, can we say what is the different type of Q A mu? Yes. So, that without going into the details, let me give you the solution, that A nu equal to minus 1 over q square J nu, where q square is essentially the momentum transfer under this one. So, what do you mean by q square? I will come to. Okay, let me just rewrite this. So, what we have is A mu is equal to minus 1 over q square J nu. So, what does that mean? This means in a region we have some electromagnetic field represented by A mu. Okay, so, it is the same index A mu, but we know that is coming from, say, some electron or a nucleus, presence of sitting electron or sitting nucleus, or moving electron or a moving electron, or some complex charge density, but that is represented by this thing. So, there is a J corresponding to this. How do we actually feel the presence of electromagnetic interactions from the charge particles? Forget about the Newtonian way of action at a distance. We demand, like in special theory of relativity, Einstein demanded that we have to have something, some cause for an effect. The effect is that we feel the electromagnetic field, the cause is that there is some charged particles moving or not moving. Now, this changes in that, or whatever the presence of that has to be conveyed to us. So, that is done by the emission or the propagation of the photons or the presence of the photons, photon field in that system. So, when for that when a photon is emitted, okay, we can think about emitting and reabsorbing etcetera, or just emitting. When it is emitted, then you will have some momentum p 1 here and a p 2 here and a q here. So, this essentially is the momentum of the q. Okay, let me don't go into further details, but essentially to complete description of the electromagnetic field surrounding this in a space configuration coordinate picture, you will have to actually take all such possible q and integrate over A, or take the Fourier transform of this A to get the spatial part of this thing, but this is basically a particular photon is represented in that way. So, this is what you have of a q. Whenever such a momentum transfer happens, you can actually think about us, or such a current happens, you can think about a photon which is represented by minus 1 over q square and j. This is what you have. Now, that and this let us look at together. For identification, let me denote this as electron 1 and the current due to that as J 1, and this as some another charged particle or electron 2, and the current due to that is J 2. This 2 has nothing to do with these 2 or these components of J. This is another some just an index to represent this particle, and then identify that that is caused by this electron, and this is talking about another electron, that is all. And now, let me look at these together. Here we were saying that an electron encountering an electromagnetic field will interact with the photon in this manner, with the current representing the charged particle motion, the current itself, electric current itself, and then this is the A mu current. Here we have the source of the current itself. So, we are saying that A mu is kind of coming from this second another electron for this thing. So, in a sense we can actually talk about interaction of two electrons as some one current J 1 mu interacting with another current J mu 2. Okay. So, this is a good picture which we have to keep in mind. So, two electrons, say electron 1 and electron 2 interacting with each other can be represented by such a picture. I mean, in actuality it is much more complex than the, but main features of this interaction can be captured and in fact calculated also in a probability for such interaction etcetera can be calculated, or the scattering of an electron on an electron to get another electron and another electron can be captured very easily by this thing. I will stop here and then we will discuss further in the next lecture.